Well, in this second order differential equation that has constant coefficients, like all of them do in this section, we're going to solve it the way we've always solved them, and then we will verify that the theorem that we saw previously also gives the correct answer. In this case, either way, it only takes a few seconds to solve it either way, really. But that's the differential equation. We're supposed to solve it and interpret it, like with a spring. So here's our differential equation, and we have initial conditions. So it's an initial value problem. We have the position at time 0 and the velocity at time 0. And let's make sure we remember what that means. I drew a little bit of a picture here. So the equilibrium would be the position 0. And at time 0, it's starting at position 1, which means we're 1 foot below that equilibrium. Now, what does this mean? The velocity at time 0 is 1. So some external force is going to give it a velocity of 1. And it's downward. Remember, down is positive, up is negative. Or it could actually be that this has been going up and down for a while, and at some point in time it's on its way down. Right here, at this point, the velocity is 1, going downward. So I wrote down the characteristic equation, which would be m squared plus 6m plus 5 equals 0. Factored it, solved it. Two distinct roots means it's the over-damped case, and we know how to solve this. We should know this by heart probably. The position at time t is c1 e to the negative 1t. Oh, let me just write negative t. Plus c2 e to the negative 5t. The negative 1 and negative 5 just came from the roots. That's the solution. We don't know the two parameters yet because we haven't looked at the initial values. But before we do that, let's take a look at what the theorem has to say about this. By the theorem, this is the solution. Well, remember, this number 6 in the theorem was 2 lambda, and the number 5 was omega squared. So what does that tell us? D is equal to, lambda would be a 3. 3 squared is 9. Minus omega squared is 5. So we get D equals 4. So this says that x of t is equal to e to the negative 3t, e to the negative 3t, times c1 e to the, d is a 4, so radical 4 would just be a 2t, plus c2 e, oh, one of these has a negative sign, right? This one of them has a negative sign. c2 e to the negative 2t. So is the theorem right? Doesn't look the same, but you can see that if you just multiply this through, you add the exponents, we would get e to the negative 3 and 2 is a negative 1. I left off the c1. c2, e to the negative 3 times e to the negative 2, add negative 3 and negative 2, and you get negative 5t. So in fact, we do get the same answer. Would have taken the same amount of time, probably. Might have saved us a second or two using the theorem. But the theorem works. All right, now let's finish this problem. We have, from the initial values, we've got, let's see, I know I'm going to need the derivative at some point to apply the second one, so we can use right here, x prime of t is equal to c1 e to the negative t, I got to put a negative sign in front of that for the derivative, and this one as well, minus c2 5 e to the negative 5t. I didn't write that very well. Could have written a 5 on the other side of that. So negative c1 e to the negative t minus 5c2 e to the negative 5t. All right, so this first one and this initial value, x is a 1 when t is a 0. So 1 equals c1 times 1 plus c2 times 1. So that's one of our two equations we'll need to solve c1 and c2. And then down here, we've got the derivative. So x prime is a 1 when t is a 0. So that would give us a negative c1 minus 5c2. Okay, so I'm going to just write that one right underneath this, and I think it'll be easy to eliminate one variable. Just add the equations to get 2 equals negative 4c2. Right, those canceled out. So c2 would be negative 1/2. Which means that since they both add up to 1, means c1 would be 3/2. So our final solution would be, I will write it, I'm going to write it way over here because I have one more thing I want to draw on the board. Final solution would be x of t equals c1, which is 3/2, e to the negative t, plus c2, which would be a minus 1/2, e to the negative 5t. So that is the solution. Okay, so using the derivative, I'm just going to find one more little question. You could say there was a part B to this question that says, find maximum displacement of the mass. So when it starts at time 0, the displacement is 1, positive 1. So we want to know how far does it ever get away from 0 in either direction. So we would take the derivative, x prime of t. Actually, x prime of t, now we actually know what x prime of t is. We actually know the c1 and c2. So x prime of t is negative c1, which would be negative 3/2 e to the negative t, x prime of t, negative 3/2 e to the negative t, minus c2, which would actually be plus 1/2, times 5, e to the negative 5t. So I'm going to make that a 5/2. So this is, here's x of t, and that's x prime of t. If we set this equal to 0, I don't have a lot of room, so I'm just going to show you that what happens if you set this equal to 0, you end up getting t equals 0.12771. I truncated after 5 digits. And we get, so what that's telling us is if this thing is going up and down, we want, where is the velocity 0? The velocity 0 is only going to be when it reaches the farthest displacement away and then changes back directions. So we've got x of t, which would be x of 0.12771. That's going to be our answer, and it happens to be 1.05614. So the maximum displacement is this value. So we can see that the velocity of 1 foot per second didn't contribute much. I mean, it didn't do too much. It started at 1 and it only pushed it to 1.05 before it reached the maximum distance away. And then it started coming back up. The graph of x of t looks something like this. It starts at 1, it goes up, and then it comes down like that. And this one is over damped, remember? So it's just going to take forever to get back down to an equilibrium spot. And this is what we found out with our computation. At t equal 0.12771, the height is, I'm not going to write it in there, maybe I'll write this as an ordered pair, 0.12771, comma, 1.05614 is that point right there. And let's observe something that we may talk about later. Our two constants, C1 and C2. Note, I'm just going to make a note for now. Note that x of 0 is equal to 3 over 2 minus 1 over 2. That was the values of our C1 and C2. Add them up and you get 1. That was the initial position by adding up those constants. Also notice that x prime at time 0 is going to be negative 3 over 2 plus 5 over 2. Which is also 1, which corresponds to the velocity. And we'll make more comments on that later.